Today, we went through superposition last week. We're just going to have a look at this week at a circuit that's got a current source in it. Just make sure we covered what happens with the current source instead of a voltage source. We're going to have a look over the next couple of weeks, Thevenins theorem and Norton's theorem as well. And to that we'll be doing complex annotation for AC analysis. So we're going to look at AC. Yeah, some extra stuff in that one, and you want that, Pete? Got that?
I must have it somewhere.
I'll just now give it to you.
This is new.
It's
new. Oh, sorry.
Does it stay together with that? Yeah, because all the theorems are in that background handout.
Yeah.
Yeah. But separate weeks, coordinates. Okay. So over the next week, 3 weeks, building up to the exam, we're going to do all of that. Yep. So, first thing I'm going to do is use superposition in that circuit to find all the currents. Okay, so that's the complete circuit. We've got a current source of 8 amps on the left hand side. We've got a voltage source of 12 volts on the right hand side, and the question saying use superposition to find all the currents. Yeah, so same as the process we did last week, we're going to develop 2 circuits, separate currents, and then add them together at the end. Alright, so circuit A, what we want to be doing is just concentrating on the current source. So what do I do in terms of superposition of the source? Why is it short? So you get rid of it. Yeah, we take it out and we put it in, but why is it a short circuit? You're right, but why do I connect, short out the removed voltage source?
Just took it out, you'd have a cap.
Yeah, okay, but when we take the current source out, we'll leave a gap. Why? Why short circuit for voltage source, open circuit, and remove the current source? Think back to last week's session. The most important thing from last week's session. Ideal resistance of ideal voltage source for short circuit, isn't it? 0 ohms. Remember that from last week? So we short it out. In our process of superposition, what do we do next on circuit A?
Label the
Yeah, we put all the currents on the circuit by normal conventions. Yeah. So we're going to have a current flowing there, and we know that's 8 amps. So that's I1A, we'll call that. Yeah. What would we expect to happen with current here in this area? No, you can't calculate it like that. Which direction would we expect it to go? And what about here? And here? Yep. Now, from that information, where can we start in terms of finding out something more meaningful? We know I1A, we already know I1A is 8 amps. What else can we find? Yeah, if we find the total resistance, how do I do that, Cal? What type of circuit have we got with them 3 resistors?
Parallel.
Are all in parallel, yeah?
That'd be all of them multiplied together over all of them added together.
No, you can't do product of a sum with 3.
Oh.
Not,
Oh,
you have to do that.
Okay.
R1 to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1 all to the minus 1. Yep, remember that one? Forgotten. So RT is 50 to the minus 1. Put the back plus 2 to the minus 1. All to the minus 1. What kind of figure are we expecting before we calculate it? Lower than? If you think about it electrically, the current's got 3 different paths to go. So the overall restriction is going to be less than the smallest one. Less than 2. Yep, so if you should get an answer to that calculation of total resistance that is less than 2. Sorry? Well, I'm getting warm now, yeah, I'm not saying hot. I'll soon brought up the temperature anyway. Right.
1.807.
Yeah, so 1.81 to 3 significant figures will do nicely. 1.81 ohms. Yep. What will that help us find? What can we find next? We now know that the total resistance of those 3 resistors is 1.81 ohms. So effectively we could say we've now got a circuit like this. 8 amps. And 1.81 ohms. It will help find which voltage count.
Wherever.
I mean wherever. We can find that voltage. Is it not equal to that voltage?
No.
And that voltage, because they're all in parallel, singly in parallel. So we find that voltage, we can then use the voltage to find the individual currents. Yeah. So what we can do is say that V2 is equal to V3 is equal to V4. So all these resistors are in parallel with each other. And it's going to be equal to all the current goes through the parallel combination, yeah, times the resistance RT. So that's 8 times 1.81 equals.
How do you...
You look,
I
see, you've reduced it, by calculating the total resistance, you've reduced it to that.
Oh, yeah, I get
Do you
it.
see that?
Yeah.
So, what we're saying is all of that 8 amps travels somewhere through them 3 resistors and ends up back here.
Yeah.
So if you find the total resistance, you can treat it like that simple circuit, yeah, and 8 times 1.81, what do you get? 14.5 then, yeah? 14.5 volts. Alright, now we know that voltage, 14.5 volts, and that's the same for all of them, because they're all in parallel. We can use that voltage to calculate our individual currents. So we can go I2A is equal to V2 over R2, that's 14.5 by 3A, V3 over R2, R3, sorry, equals 14.5 over 30 ohms, whatever that is, and then I4A is V4 over R4, 14.5. I think that's 7.25, is it not? The other two, I got 0.4 and 0.29. And the check is, gentlemen, check on those 3 currencies, and they should equal 8 amps there or there, allowed for random hours. Yep. All got that? I'm not recording. I got it in mind. That's 10.84 volts.
Right, what did you call this? ES? What's that stand for again?
That's the battery.
Oh, okay.
Yeah.
Oh, yeah.
Yep, because that's what's pushing the current through, isn't it? Yep. And then, now on that, we can now find I2B, which is equal to that VR2 over R2, that's 10.84 over 50. .22 amps, and I3B VR3 over R3, 10.84 over 30, 0.36 amps. Yep. So now we know all the currents for circuit B. We can add them to our original circuit. So let's do that in red. So I1B is 0 amps. I2B is 0.22 amps. I3B is 0.36 amps, and I4B was 0.58 amps. Yeah. And then this one is obvious. 8 amps in that direction, no amps in the other. So overall, 8 amps flowing there. Because they're both in the same direction, what do? Add them together. So it's I1, I2A, plus I2B, that's 0.29 plus 0.22 equals 0.51 amps. So we've got an overall current down there of 0.51 amps. This is going to add together too, so it's 0.48. Plus 0.36, .84 amps, and then because the two I4s, hang on, what's wrong with I4B? Yeah. Because they're opposite, what we got to do, take the smallest one away from the largest one. So I4 overall is I4A minus I4B. That is 7.25 minus 0.58. 6.67 amps. In the direction of I4A. So it's charging that battery at a considerable rate. Nichols. When I get round to it, I'll put all this stuff up on bright space anyway, but... Yeah.
It's only got another colour.
Just write that again and make it neat. Alright, so that just, I thought I'd better cover a circuit that had a current source in it, because that involves us in when we did circuit B, in actually leave an open circuit as opposed to a short circuit. Alright? Yeah? I can move on now then, yeah? Good. Right. What we're going to look at now is another theorem, okay, called Thevenins theorem. This one and Norton's theorem are particularly useful where you want to, where you might want to analyse what a circuit do if you changed one of the components. You had a particular load resistor in mind, but you wondered how that circuit was going to respond to, let's say, a 30 ohm, a 50 ohm, and a 60 ohm load. Because you can do the complex calculations once, and then with the simplified Thevenins or Norton's equivalent circuit, easily calculate the values, currents and voltages for the different load resistors. Okay? Not so useful where you want to know all the currents in a circuit because you're simplifying for one particular interest load resistor. Alright? So we're going to do this Thevenins theorem now. In words, Thevenins theorem says any active network having two terminals I and B can be replaced by a constant source of voltage V little t, V Thevenins, and an internal resistance. The value of V Thevenins is equal to the open circuit potential difference between the terminals A and B, and the value of the resistance of the network, RT, R little t, is measured between the value the terminals A and B with the load disconnected and all sources of voltage or current replaced by that ideal internal resistance. What a wordy statement that is. Do you understand that? I bet you don't. Right? I'm not going to ask you to write that out. What I am going to say, and I haven't said it about Thevenins, is where you're asked to do these theorems in the exam, you're going to be expected to sketch the circuit of each stage and explain why you're replacing the voltage source with a short circuit, or so you're expected to explain the process as well as do the calculations. You won't get full marks if you don't explain each step of the process. Alright, so what I've done is summarised a procedure to adopt when using Thevenins theorem. First of all, you remove the required load resistor from the circuit, for which you need to analyse the current from the network. That leaves two terminals open that you can label A and B. So you take the resistor of interest, the load resistor, out of the circuit, leave the open terminals and mark them A, B. You then use normal techniques, so that could be, certainly going to be Ohm's law, series parallel resistance. If the network's got more than one source, you might have to mix in superposition there as well, okay? But you use other techniques to find the open circuit voltage between the two terminals A and B. That voltage is just what's called your Thevenins voltage, and I'd call that V little t. Then you remove each source of voltage or current and replace that source of voltage or current with its ideal resistance. So thus you replace a voltage source with a short circuit, you replace a current source with an open circuit, and then you determine the resistance looking back into the circuit from the terminals A and B. Right. And what happens then is you can use that equivalent circuit, so you'll end up with a V little t and an R little t. You'll connect your load resistor back to this terminals A and B as a simple series circuit calculation to calculate the current, voltage across, and so on. That is best served by an example. But what Thevenins theorem, for example, does is turn that into that. So we've got 1, 2, 3, 4 resistors. If we're interested in what happens with this as our load, we do Thevenins on all of that, and we end up with a V little t, Thevenins voltage. It won't be the same as that 24 volts there. Okay? And we end up with a resistance R little t, Thevenins resistance. No resemblance to any of the resistor values in the circuit necessarily. And we can connect back our load to the two terminals A and B there, that being our load that we're interested in. We can then calculate the current through, the voltage across, the power dissipated, and so on. And this circuit here will work exactly like all of that bit. If I put a 50 ohm in there, or 60 ohm, or 150 ohm, so I can then analyse that network for different size loads. Yep. Okay. So we'll do the complex correlations once, and then we can analyse for different values load resistor. So, what we're going to do is use Thevenins theorem to calculate the current flowing in the power dissipated in this 30 ohm resistor. So we're going to focus on this R4 here being the load resistor.
Why do you label them R1, R2, R1, R4?
That's a misprint that's been there a long while. Alright? Sorry. It's not a deliberate mistake. Alright? So we're going to use Thevenins theorem to calculate the current in this resistor here, R4. Yep. So what we do is we take that resistor out. Okay, we label the open circuit terminals A and B, and this, if we can calculate this VOC here, that is equal to the Thevenins voltage. So how can we do that using normal methods? What can you see there that we can calculate?
Voltage across R1.
How do I calculate that now with the information I've got?
4 over 5.
Is the 24 volts wholly across R1 and nothing else? No? Okay.
R2.
Just think about current for a minute. What currents have I got flowing in this circuit? Some will come up and put current hours on that circuit for me.
It's going to work.
Yeah. Just the hours. Yeah, I'll go with that.
That's all, isn't it?
Right. How much current is flowing, if we call that, hang on, let's just correct my error, R3, how much current is flowing as I3 in the circuit at the moment, at this instant in time? nothing. Yeah? Because that leg through R3 is open circuit, yeah? And no current is flowing through that 5 ohm resistor. Yeah? Therefore, that is 0 volts. So in terms of current, can you see that all we've got at the moment is this loop around these 3 components? Yeah? So if we call, there's only one current, and if we call it I, yeah, how do I calculate I?
Work out what those two resistors equal.
Yeah, we can do it all in one go, can't we? We can do VS over the total resistance, which is R1 plus R2 because they're in series. Yeah. So it's 24 over 25. .96 amps. What will that now allow me to do? Afterwards. Explain.
Negative divided by I.
I now know the current going through the 5 ohm and the 20 ohm resistor. So what can I calculate? Volt drops across those 2 components. Yeah? So if I want to know this one,
I times V. Yeah, I times R.
yeah, so we can do VR2 is I times R2, 0.96 times 20 equals 19.2 volts. Agreed? Yep. Now, how does that help me? 19.2 volts. What have we got now that we didn't have before we had that? Yeah, we could find that, but we don't really need that to do what we want. Then you could find that from that all the voltage across this one. But what have we got over here in terms of voltages? No, 24 don't come into it. What we got here in terms of voltages?
We take that component out is parallel to that, so that
What is that?
VOC.
Yes. If you look here, we've got Kirchhoff's voltage law. We know all the voltages in that. We know this voltage. We know that one. We know that one. So technically, remember, clockwise arrows one side, anti-clockwise arrows the other. So we've got clockwise arrow in 19.2. So we can go by KVL, VR2 is equal to VR3 plus the open circuit. Yeah, because that's 0, we're saying 19.2 is equal to 0 plus VOC, therefore VOC is 19.2. So our Thevenins voltage, which is the open circuit voltage, is 19.2 volts. And that's because you're not losing anything in the top R3 resistor because there's no current flowing through it. So that and that are effectively in parallel, and that 5 ohm resistor under these conditions is doing nothing. Yeah, all understand that? Not all circuits will be like that. They could be different. Techniques needed. Okay? So therefore, Thevenins voltage V little t is 19.2 volts. Alright? We go forward a minute to there. Hang on. Another slide in here. We start our Thevenins equivalent circuit. We're going to have a voltage source, VT, 19.2 volts. We're going to, in a minute, calculate, look at that change to red, R little t, and our 2 terminals, I and B. We'll connect our load to eventually. So we've calculated V little t is 19.25 volts. Yep. Now we need to find the value of this resistor and source, R Thevenins. And the way we do that is we take out the voltage source and replace it with its the internal resistance of an IC voltage is a short circuit. And then we calculate the resistance R little t looking back in at the terminals at A and B. So that's my very poor drawing of an eye. But we're going not with respect to the voltage source like before, but with respect to the 2 terminals. So what would I measure if I put an ohm meter across those 2 terminals? No, the 2 terminals are open circuit, but you need to look at where there's a route for current. Current can go up here, down there, all down there, and back here. So what kind of circuit have we got? How can I calculate R little t? Bear in mind, again, correcting my field card, that's R3.
R3 plus R1.
Yeah, product over sum, because we got R3 is in series with R1 and 2 in parallel. Yep. So it is R3 plus R1 times R2 over R1 plus R2. 5 plus 20 times 5 over 25 equals 9 ohms. Is it 9 ohms? Yeah. Okay. You are like calculators. You're like slide rules. That's what we used to use before calculators. You never say a slide rule. No, I work like a bit like a vernier caliper. You can do calculations with them. So like rules, things that slide within each other, and you line them up. And then you used to have a book with tables of all logarithms and sines and cosines and their inverses, so you could look them up. Yeah. No, well, I'm not against modern tools, but I'm just saying, you know, in them days you had to use other methods. Right, so what we have now is the complete equivalent circuit, with that being 9 ohms, and we can connect our interested load resistor, 30 ohm resistor, back across the terminals A and B, and we can find the current IL, and we can find, once we've got the current, we can find the power. And we can say, so we can say IL is equal to what?
What is the PL?
Yeah, that's the power. The question asks for the power dissipated as well. How do I calculate IL?
19.25.
Yes, it's, in terms of our quantities, it is 3 Thevenins over R Thevenins plus RL. Yep. You can do 0.25 over 9 plus 30 equals. Where did I get to 19? Was it 19.25 or 19.2? 19.2. So where I got 0.25 from, I don't know. Just correct that. That came out for me at 0.49 amps. And then we can use that. How can I calculate PL from that current?
What's RL?
It was the load resistor, the 30 ohm resistor, yeah. How do I calculate power? Can't use that voltage. Information I've already got. We've got three formulas for power. I squared I. So it'll be IL squared times RL. 0.49 squared times 30. .27 watts. Right. Are you okay with that, guys, or not?